We are Team Fit and Go, and our project is the Universal Drone Mount. The current scene of the UAV sector is fragmented in terms of compatibility between different applications across different industries. With many manufacturers striving to reach vastly different results with their designs, there has been very little standardization across different platforms. Furthermore, the UAV system available in the market are designed for specific applications and are not able to do other tasks. Essentially, each manufacturer is building purpose-built drones with no plans for customizability. And it should be noted that the drones that are being discussed are not the drones that a consumer could walk into a store and buy. Those are very light and maybe could hold something up to 1 to 2 pounds. This project aims to cover Class 2 drones, which weigh at least 20 pounds and have potential to do real meaningful work, besides just being a camera. The main goal of this project is to design and prototype a versatile universal mount that would allow future drone applications to attach to any drone airframe and rapidly deploy those applications. Also, this universal mount can drive industry standardization where it would be a common feature in airframe design in the future. The success of this project would help inspire and develop a new VIP team at Georgia Tech, where students can design all kinds of different applications and deploy them on any airframe that they would want. The main challenges that were encountered were compatibility, predicting potential use cases, future regulations, and narrowing the project scope. Compatibility mainly means the compatibility between different airframes or different airframe manufacturers. Predicting potential use cases were difficult, because if some application may or may not be suitable for drones, there really isn't a way to check because the industry doesn't exist. And since Class 2 drones can't be bought by regular consumers yet, there isn't really any concrete rules or regulations, so placeholders were created in order to constrain the design, and these were very difficult to come up with. Next, since a lot of our preliminary outlines are very wide and encompassing, narrowing the project scope to a single design or one aspect was also very difficult.
The goals of the design including supporting payloads up to 75 pounds within a 12 by 12 by 3 inch envelope. The design should also allow electrical and data connections and be robust and interchangeable with different types of payloads. Although several design alternatives was introduced, 3 designs, the Quick Connect, the Rail Hybrid, and the Pylon was determined to be feasible and evaluated based on customer and engineering requirements using the evaluation matrix. After the evaluating process, the Pylon design was chosen and the team advanced to the prototyping process. Using 3D print process, many prototypes revision was tested and evaluated. 3D printed scaled-down version allowed the team to quickly and efficiently test new design features, locate design flaws, and correct them on the next revisions.
In the proposed solution, the payload is mounted onto the underside of the blue rail, and the gray pylon is mounted onto the drone. The user will align and slot the rail into the pylon to attach. This one motion accomplishes 2 tasks. The latch will mechanically lock into the striker, and the electrical connections will be coupled together.
The most critical function of our design is to create a secure mechanical connection between the drone and the payload or application. For inspiration, we look to pylons found on military aircraft, which are able to hold heavy artillery while restricting movement and minimizing vibrations. Our version of the pylon design resembles a rail that allows for easy coupling. The payload is held in place on the rail by a spring-loaded rotary latch that locks onto a striker. The latch can quickly be decoupled with a push-button release.
The power and data connection between the drone and payload is made through a set of 8 pins, including 6 data pins and 2 higher voltage power pins. This design is inspired from a traditional power tool battery connector. The 2 halves of the connector slide together at the end of the operation of the mechanical connector, ensuring everything is properly aligned before any force is applied to the pins. The pins act as a breakout for a microcontroller, allowing for data and power to be sent between the drone and payload. Our current prototype uses a salvage power tool battery for the connection pins and an Arduino for the microcontroller.
To validate the designs, finite element analysis was conducted on the pylon, striker, and rail. All of these parts were modeled out of aluminum 6061, which has a yield strength of approximately 276 megapascals. A factor of safety of 2.0 was chosen, meaning that the applied load on the simulations was 150 pounds of force. In all three cases, the internal stresses fell way short of the 276 megapascals, which was the yield strength. This means that there is room for redesign to reduce both weight and optimize the shapes. To validate the electrical connector, a voltmeter was used to test the signal integrity of each pin. Once the integrity of each pin had been verified, we were able to implement a test application using an ultrasonic sensor, an LCD display, and a buzzer. When the payload was connected, the buzzer would go off, letting the user know with an audio cue that the connection was sound. From there, the ultrasonic sensor would detect values and display them on the LCD. This whole application was meant to simulate drone-to-payload communication.
In the near future, the pylon geometry will be improved in order to minimize weight and maximize aerodynamics. The proposed solution will be used to launch a new, vertically integrated project here at Georgia Tech where students will develop drone applications. Finally, the platform will be introduced to drone manufacturers to implement as a standard coupler between UAV systems and applications.